Okay, so hello everybody. Welcome to this session, or welcome to this problem solving session. It's our week 6, and last week you have covered steady state error, and also root locus was introduced to you. And in today's lecture, we are going to solve questions based on the steady state error and root locus. Uh, I assume if you're joining this session, you have already gone through uh, the slides, the lectures of the previous week, and also attempted the assignment. Then this session will be fruitful. So basically, what we will be doing today, I'll just briefly give you an overview of steady state error. So, and then we will solve some questions, and uh, then we'll jump to root locus. So, yeah, by the time others join, we can do this thing. So, I think the previous or a week before that, we discussed time response analysis, where we discussed rise time, we discussed peak time, we discussed overshoot, we discussed uh, delay time, etc., etc. So we studied the response of a second order system, and we studied about these properties. So these all properties, they are transient properties. They are transient properties. And when we talk of settling time, or there is another term, which is the steady state error, this comes in the steady state regime. So these are transient properties, and we will also be seeing today about the steady state properties. That is, when the response has settled. For the completeness, I'll just make the response. So, for example, I have an underdamped system. This is my time. This is my response, C of t, and for a unit step input. And let's assume my reference value is this. And my response will be something like this. Wait. Okay, so we get a response like this. Then we have rise time, peak time, overshoot, here, rise time, etc. So they were all transient properties, like what happens just in the beginning. Then after the response has settled, we can see settling time, TS, and we can see steady state error, which is denoted by ESS. Now, what is steady state error? So let's assume my reference is 1 here. And if my output is exactly tracking this reference here, then I can say there is no error. There is no error in the steady state of the system, or there is no steady state error, right? Or in other words, I can define the steady state error, ESS. It is the difference of my reference signal minus my response. This is actually error, difference between my reference signal and my response. But as t tends to infinity, then I get steady state error. So this is error. As t tends to infinity, I get steady state error. So in the error, I put t equal to infinity. Then see what happens. So t equal to infinity means somewhere when the response is settled, I get what's the difference between my response and my input and the response. That is error. Now you see that as of now we're dealing with transfer functions. So we don't deal things in time domain. We can basically do this. It's not a big deal of calculating error in time domain. Then if given a transfer function, we'll find inverse Laplace, then we can get something in time domain, then put equal to infinity, we'll get error, etc., etc. But that will make our things complicated. So it's better to do things in S domain itself, right? So in S domain, there is a formula for steady state error, which is given by final value theorem, which is actually derived by using final value theorem, which is given by limiting S tends to 0, S into R of S divided by 1 plus G of S H of S. Or sometimes, since this G of S H of S is OLTF, it's an open loop function I've discussed in detail in the previous lectures. So then this steady state error, we can calculate this. It's S into R of S. R of S is the input. And then we, in the denominator, we have 1 plus G of S H of S or 1 plus OLTF. This formula is very, very important. You should remember it, right? So this is a very important formula, and basically we'll be using this formula. There are many other ways as well of solving the questions based on steady state error, but yeah, this formula comes very handy, right? Now the steady state error, it actually depends on the type of system, right? It has nothing to do with order of the system. If you take different orders, if you take systems of different orders, you'll see the steady state error. If it is finite for a second order system, it will be finite for a first order system as well, if it is the case. So, but it actually varies with the type of system. I have already discussed what is type, what is order. So repeating it once again, type of a system is the number of poles at origin in the open loop transfer function. So there is one table which is very, 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 very important. That's why I have given triple star here. So it's very, very important as far as the exam is concerned, your exam is concerned, as well as gate is concerned. This comes very handy. You can straight away, if you remember this table, you can straight away solve questions based on steady state error. You'll be just seeing in a minute. So what is this table all about? I'll just explain. See, I have type 0 system, I have type 1 system, and I have type 2 system. I told you the steady state error, it varies. It actually depends on type of the system. So if you and what I have on one side I have type of the system, and on the other side I have different inputs. So the steady state error, it depends on the nature of inputs as well. It depends on the type of system. Okay, so it depends on the type, it depends on the nature of input. So that's why I have different inputs here. I have a step input, I have a ramp input, I have a parabolic input, all of magnitude A. Okay, if I say I am giving a unit step input, then this A will be 1 here if it is unit. Similarly, if it is unit ramp, then here A will be 1. If it is unit parabolic, then A will be 1 here. Otherwise, how much is the amplitude? It will be specified accordingly. You will have to take this A, and that's why I have given the inputs in terms of A, in terms of the amplitude. Okay. Now see, when you have a type 0 system, this entry, you see this entry, when you have type 0 system and step input, then your steady state error is this. What is your steady state error? It is A divided by 1 plus Kp, where this Kp is positional error constant, and which is given by Kp is equal to limiting S tends to 0, G of S, H of S. Okay, so whenever you have type 0 system and you have a unit step input, there will be some steady state error, and which is given by A divided by 1 plus Kp. So basically, yes.
Unable to see your screen, sir.
Is it with anybody else as well? Can anybody confirm? Suraj, it's visible to Suraj. Is it visible to Shubham as well? Yeah. You can just like exit the meeting and join again. Maybe it's a network issue or something.
Okay.
Okay. So Okay, so basically, if you have a type 0 system and you are giving a step input, you only have to find this positional error constant. Then your steady state error will be A divided by 1 plus Kp, where A is the magnitude of the input signal, amplitude, sorry. If you have a type 0 system and you are using a ramp input, the steady state error will be infinite. So it doesn't take this type 0 system doesn't take ramp input. You can also test this in MATLAB. You can uh, create a hypothetical type 0 system and then give it step input and then give it ramp input, then give it parabolic input. You'll see for a unit step, the response will be finite, and for ramp and parabolic, it will go to infinity, will be infinite. So I'll not waste much time on this table, but just make sure that just remember these three things. When you have a type 0 system, the steady state error will be finite only for a unit step, only for a step input. If you have a type 1 system, the steady state error will only be finite for a ramp input. If you have a type 2 system, the steady state error will only be finite for a parabolic input. Okay. And for type 2 system, ramp and step will be 0. And for type 1 system, step input will be 0. And for parabolic input, steady state error will be infinity. Then you also have this velocity error constant and acceleration error constant, because sometimes you're directly asked find acceleration error constant or find velocity error constant. Or when we design the controllers, when we design the compensator design or lag compensator, lead compensator, there you will see this velocity error constant is given, acceleration error constant is given. That's why it's very important to remember the expressions for them as well. It's very easy for positional error constant, it's S tends to 0, GSHS. Then similarly for velocity error constant, it is S tends to 0, S into GSHS, and for acceleration, S square into GSHS. You can also remember it like this. It is d by dx by dt. Then this is d2x by dt. 2, if it is, there is no S here, and here we're differentiating. So one S comes, then you're again, sorry, you can remember it like this. If it is x, position, if it is x, then this will be dx by dt. So one S will come. This will be d2x by dt2. Another S will come. This is the way to remember it. Okay. Now, I hope you remembered this thing, that for a step 0, for a type 0 system and step input, steady state error is finite. For type 1 system, ramp input, steady state error is finite. Type 2 system, parabolic input, steady state error is finite. Now let's directly jump to the problems. Okay, we should take time to read the problem, because if you read the problem correctly, your 60% problem is solved. So normally what happens in exams, we sometimes read problems in a hurry and then end up solving them incorrectly. So it's better to take 2 minutes to read the problem and then solve it correctly, rather than interpreting it wrongly and solving it incorrectly. Anyway, so we are given a unity feedback. So you have to mark these things which are important. So you are given a unity feedback. So unity feedback is important. You will underline it. You are given a transfer function. Okay. Uh, and you are asked what should be the value of k. So we have to find the value of k and a to obtain a steady state error of 0.2 for a unit ramp input. See, so steady state error is finite. Okay, steady state error is finite, and but when we are applying a ramp input. Okay, so steady state error is finite on a ramp input. When is the steady state error finite for a ramp input? Then what is the type of system from this table? Anybody? Anyone? What is the type of system from this table? Type 1. It's type 1. So the system is type 1. It means what is the value of A? since ESS is finite for a ramp input, it implies it is a type 1 system. Type 1 system means this value should be 1. It implies my A is 1. Why? A1 means type 1, and that means we have one pole at the origin of an open loop transfer function. So our two options are eliminated. This option is gone, and this option is gone. Right? Now, now let's solve the other part we found. So now our transfer function is g of s is equal to k divided by s raised to the power 1 into s plus 10. Okay. And what we have to find, we have to find the value of k such that my steady state error now, also it's given steady state error is 0.2 for ramp input. But it's written unit ramp input. It means A is 1 here. So my ramp input, my A is 1 here. Okay. Now let's apply. So what we have to find k? We have to find k. Now what is the formula for steady state error? I'll just write that formula. My steady state error is limiting s tends to 0, s into r of s divided by 1 plus g of s h of s. Okay. Now you see it's given in the question, it is unity feedback. And if it is not mentioned positive or negative, obviously you have to take negative feedback. So it's unity, it means my h is 1. So my h of s is 1 because unity feedback. So let's then try to solve it. It will be limiting s tends to 0, s into, this is a ramp input. Okay, so ramp input, for a ramp input we have, for a step it's 1 by s, for a ramp we have 1 by s square. By why? Because it's unit ramp. So r of s is 1 by s square, then divided by 1 plus what is g of s, that is k divided by s into s plus 10. Now let's solve it. Let's solve it a bit. It will be limiting s tends to 0, s divided by s square, or 1s and 1s and 1s goes. So it will be 1 by s, and this will be s square plus 10s plus k divided by s into s plus 10. This and this goes, and this steady state error is equal to 0.2. Okay, now let's solve it. So it will be limiting s tends to 0. I'll take this s plus 10 on the in the numerator. It will be s plus 10 divided by s square plus 10s plus k equal to 0.2. Put s equal to 0. I'll get 10 divided by 0 plus k equal to 0.2. It implies my k is 10 by 0.2, which is equal to 50. And the option number A is correct. Anybody has any doubt in this question? I'll just revise it, what I did. So first we have to carefully read the question. So in the question, we have to identify what are the key terms. Unity feedback is key term. It means h of s is 1. We have given an open loop transfer function, and we have to find the value of k and a to obtain a steady state error. This is important for us, steady state error of 0.2 for a unit ramp input. So we know for a unit ramp input, steady state error is finite only for a type 1 system. That means we get the value of A equal to 1 because for a type 1 system, only one pole of the open loop transfer function lies on the origin. Okay, and after that, we have to find the value of K such that steady state error is something. So we will directly apply the formula for steady state error, which is given as 0.2. So that's what I have applied. Just applied the formula. It was given that unit ramp is applied. So R of S is 1 by S square. Then I just put in the values and got the answer. I hope things are clear. Now, if that is clear, let's solve this question then. So see, there are two questions actually. This is the first part of this question, and there is another part after this. So a feedback system employing output rate damping is shown in figure. So we have this figure where there is some feedback control system. And what's the question? The question is, in absence of the derivative feedback, you can see here, this is derivative feedback. Why? You have S into K naught. So S into K naught, it's a derivative controller. So you have this in feedback. It means this is a derivative feedback. So in the absence of, so the question is saying in the absence, in the absence means this K naught is equal to 0. There is no this feedback. There is no feedback. In the absence of this derivative feedback, the steady state error resulting from a unit ramp input is. Okay. Now see, again, we have unit ramp input. It means R of S is 1 by S square. Okay. So it is also given, we have to find the steady state error. And if we look from the options, the steady state error is finite, means clearly it is a type 1 system, and that is visible from the transfer function as well. So you see this transfer function, this is S into S plus 2. So there is only one pole at the origin. So this is type 1 system. Okay, makes sense. Why? Because for a type 1 system and unit ramp input, steady state error is finite, which is also visible from the options. Now what we have to find? We have to find the steady state error and when there is no feedback. So see, when there is no this derivative feedback, let's assume when there is no derivative feedback, this term is not there, then this transfer function reduces into something like what will be our g of s, h of s then? See, in absence of derivative feedback, what will be our g of s? Our g of s will be 10 divided by s into s plus 2. Okay, because this is in cascade. So they will be multiplied when there is no feedback. So then we get then we get g of s as 10 divided by s into s plus 1. Okay, now what we have to see, you can see you can see clearly from here, it is a unity feedback. So h is 1, our h of s is 1. Then let's find the steady state error. Our steady state error is limiting s tends to 0, s into r of s divided by 1 plus g of s h of s, which is equal to limiting s tends to 0, s into 1 by s square, because we have a ramp input. 1 plus, what is g of s? 10 divided by s into s plus 2 into 1. H of s is 1. Let's simplify it a bit. So this s and 1s goes. So it's the calculation is somehow similar to what we did in the previous question. It will be 1 by s whole divided by, I'll just do this cross multiplication, it will be s square plus 2s plus 10 divided by s into s plus 2. This s and this s goes. We get limiting s tends to 0, s plus 2 divided by s square plus 2s plus 10. Just put in the limit, you get 2 divided by 10. ESS is equal to 2 divided by 10. So 2 divided by 10 means 1 by 5, or it implies ESS is 1 by 5, which is equal to 0.2. Okay, so any doubt here? So if we see the options, then C part is the correct answer, 0.2. The steady state error is 0.2. Now in the same question, let's see the second part. In the same question, let's see the second part. Now find the derivative feedback constant K naught. So now we have to consider this loop. And we have to find this K naught. Okay. Okay. So find the derivative feedback constant K naught, which will increase the damping factor of the system to 0.6. Very good. So we have to note important things here. So our first part of the question is, we have to find K naught such that damping factor, we know damping factor is 0.6. Perfect. Then in the second part, with the obtained K naught, what is steady state error resulting from unit ramp reference input? Fine. So first we have to find this K naught, and after this we have to find the steady state error resulting from a ramp input. It is unit ramp, so we take 1 by s square. So after this we have to find steady state error for a ramp input. The question is very interesting. Why? Because we just have to solve the loop. That's it. That's the main concept behind it. So first of all, what we will do here, let's try to solve this. Let's try to solve this loop. Then we will get some transfer function, because this is a negative feedback. And that transfer function we will multiply with this 10, and then again take the unity feedback. That will be our resultant closed loop transfer function. So why we will get a closed loop transfer function here? Because I have zeta. Zeta is given. So I know for a second order system, I have standard form omega ns. This is characteristic equation, and omega n square, or the transfer function, it will be omega n square. So Cs by Rs, standard transfer function, will be given like this for a second order system. So we will also find this from the block diagram. So try to remember what I'm saying. So from this block diagram, we will try to find the second order transfer function. And then we will compare these two transfer functions. We'll get some values, and from those values, we should be able to find the value of K naught. Okay. Now, first of all, let's solve that loop. Let's solve this loop. So we have, this is G of S, this is H of S. So we have for this whole loop, let's name it as G1. G1 will be 1 divided by S into S plus 2 whole divided by 1 plus 1 divided by S into S plus 2 into S into K naught. I'll write it here. So let's say for that small loop, it will be, okay, what was that? I forgot. 1 divided by S into S plus 2. 1 divided by S into S plus 2, this is G of S, divided by 1 plus G of S, H of S. S plus 2 into H of S is S into K naught. Perfect. Now let's try to solve it a bit. So g of 1 is equal to 1 divided by s plus 2 into s whole divided by s square plus 2s plus sk naught divided by s into s plus 2. This and this goes. My g1 of s will be 1 divided by s square plus 2 plus k naught into s. This is my g1. But you see, this g1 is in cascade with 10. So my net resultant open loop transfer function, which is g2, will be 10 into this g1. So my another transfer function, which I will name as g2, will be 10 into g1, which is equal to 10 divided by s square plus 2 plus k naught into s. Perfect. Now I will solve this loop. Now I got something like this now. I got something like this now. There is some input. I have my G2, then this is output. There is unity feedback. So I got something like this. This can easily be solved. So let's assume my what is my output? Output is theta C and theta R. So my theta C over theta R will be G2 divided by 1 plus G2 into 1. So when we solve it, we get very simple 10 divided by s square. If you have any doubt anywhere, just stop me and ask. S divided by 1 plus s square plus 2 plus k naught into s. Yeah, that's it. Sorry, it will be 10 divided with this. Okay, then if we solve it, we'll get 10 divided by s square plus 2 plus k naught into s plus 10. Again, I told you this is the transfer function that I got from the circuit, from the feedback loop. Now you also know for a second order system, the transfer function is omega n square divided by s square plus 2 zeta omega ns plus omega n square. Just give me a second. Okay, so this is my second order system. So now let's compare. So it means when we compare, we get omega n square equal to 10. It implies my omega is around 3.16. Okay, and after this, my 2 zeta omega n is equal to 2 plus k naught. My 2 into zeta is given as 0.6 and omega n we've just found as 3.16 is equal to 2 plus k naught. Everything is given. It implies my k naught is equal to 1.8. So if you see, your two options are eliminated, this and this. Now our steady state error is either 0.53 or 0.38. Okay, so now let's find the steady state error. It's very easy now. So we got this. Now what will be my steady state error? Limiting s tends to 0, s into rs. It comes very handy, this formula. G of s, h of s is 1, and this r of s is a ramp input. So we'll just put limiting s tends to 0, s into 1 by s square divided by 1 plus. This is, we have to see the open loop. We have to see the open loop transfer function, which is this. Okay. So it is 10 divided by s square plus 2k naught into s square plus 2 plus k naught into s. Okay. So just solve it. So 1s and 1s goes. So we get ESS equal to limiting s tends to 0, 1 by s divided by s square plus 2 plus k naught into s plus 10 divided by, this whole s square plus, or I can write it like this, s into s plus 2 plus k naught. Okay. This s and this s goes, can write it as s plus 2 plus k naught divided by s square plus 2 plus k naught into s plus 10. So when we put s equal to 0, when we put s equal to 0, we will get 2 plus k naught by 10. I know the value of k naught. K naught is 1.8. So it is 3.8 divided by 10. So my steady state error is 0.38. Anybody has any doubt here? So the option is B option is correct. Please ask. If you have any doubt, we can discuss in this question. This is a very good question where actually nothing is given straight away and it looks very difficult at the first sight. So where was the question? Yeah, this question. It looks very difficult at the first sight, but it was not that difficult. We just have to, I told you last time as well, whenever we have this block diagram or there's something in feedback, even try to solve the loop, try to solve it, and then things will be very easy. Things will be visible actually after that. So if you have any question, please ask me, or you can just solve another question. And I would want you to solve this. It's a very easy question. Please, everybody, please attempt this question. Please attempt. Take 2 minutes and please try to solve it. We're given RT is 0. You have to identify actually that what is given. Is it ramp input, unit step, or anything? What is given, you have to identify. Given 0.1 into t. And it's desired that steady state error should be less than 0.005. So steady state error should be less or equal to 0.005. The complete range of value of k for error to be within the specified limit for a given system and for unity feedback. So you are given a unity feedback and you are given a system. So let's try to solve it. You have a system g of s, or you can also solve it s into s plus 1. Again, it's a type 1 system and you're applying a ramp input. The steady state error has to be finite. Okay, so now directly we can apply the formula because we have to find the steady state error, and then at the last we will impose this limit. Okay, so my steady state error, just the formula. I'm writing formula again and again so that you remember this formula. 1 plus g of s h of s. Since unity feedback is given, it means this h of s is 1. Now let's put in the values, limiting s tends to 0, s into r of s is given as 0.1 into t. When we take Laplace of it, it will be 0.1 divided by s square whole divided by 1 plus, what is g of s? K divided by s into s plus 1. Very good. Now let's try to solve it. Again, this 1s and 1s goes. We have limiting s tends to 0, 0.1 divided by s whole divided by s square plus s plus k divided by s into s plus 1. This s and this s goes. We have limiting s tends to 0, or I can write steady state error is given by 0.1 into s plus 1. I just flip it, s square plus s plus k. Now let's put in the limit. So this will be 0.1 divided by k. This is my steady state error, 0.1 divided by k. Okay. Now it's given steady state error has to be less or equal to 0.005. It means my k should be greater or equal to 0.1 divided by 0.005. If you simplify it, you will get the k should be greater or equal to 20. And this is the answer. Any doubt? Any doubt in this question? Please, anyone? If you have any doubt, please ask. Anyone? If you do not have any doubt, then please solve this question. I'll just give you a question and tell me the answer. You should be able to solve this question. I'm giving you a block diagram. I'm giving you a block diagram. I'm giving you a unit input. S plus 15. Basically, there is a controller, and your system is 15 divided by S plus 1. This is your output, y of t. And you have a unity feedback. Perfect. So you are given this system, and I said I'm applying unit step. Okay, unit step is applied. So find the steady state error. Find steady state error. Everybody please solve it. I'll give you options. 25%, 75%, 6%, 33%. Please solve it, everyone. Anyone? Suraj has solved it. 0.25. It means 25%. Anybody else? Shubham? Should I solve it? Very simple, actually. What you have to do, just write the net transfer function. So a net transfer function, I will name that as g of s, which will be 3 divided by s plus 15 into 15 divided by s plus 1, which is equal to 45 divided by s plus 1 into s plus 15. Perfect. And what is h of s? H of s is 1. And now, this is, again, you can use the same formula. What is steady state error? Limiting s tends to 0, s into r of s divided by 1 plus g of s, h of s, which is equal to limiting s tends to 0, s into 1 by s, this and this goes, divided by 1 plus 45 divided by s plus 1 to s plus 15. And then if you solve it, you'll find 0.25, which is equal to 25%. The option A is correct. Anybody has any doubt in this? Then I can solve it again, like completely, if you want me to do. Okay. Any questions until here? Otherwise, you can just move to root locus. Anyone? But this is a very, very important topic. You know, a lot of questions you'd be getting in your final exam, and you will also see these steady state error questions. They are linked with controller design. So when you are designing a lag compensator, lead compensator, or a proportional controller, or whatever, you often see settling time and this steady state error. And so basically your goal is to minimize it. So when you are designing a controller, you will minimize this steady state error. So you will often use this formula very often in your next upcoming weeks. Very often you will use this formula. So that's why it's very, very important to have a very good understanding of this topic. So I hope this is clear. Now let's move to the root locus. Let's move to root locus. I also assume, as I told you in the beginning, I also assume that you have gone through the lectures, you have gone through the slides, you have gone through the assignment questions at the least, because then and only then and only we can, have these sessions. We can make these sessions as interesting as possible, as interactive as possible at the same time. So what is root locus? So we studied Rout-Howitz criteria last time. Okay. So in Rout-Howitz criteria, we saw that a system is stable, marginally stable, or unstable, right? And that depends on the number of poles on the right half plane, in the right half plane. And we also saw that systems are stable for a range of values of k. That's the gain. And we also saw here today itself that for some range of values, we have this steady state error. So of course, the system has to be stable. Then only we can find the time response analysis. If the system is unstable, there is no like there's no sense of doing that time response analysis. So in root locus, basically we vary a parameter, and in this case, that is the gain k, and we vary that from 0 to infinity and see what is the locus of our closed loop poles. So formally, if I have to define this, the definition is very important because uh, that solves 30% of this root locus stuff, right? So root locus, I'll just write it. Root locus is defined as the locus of points, the locus of closed loop poles obtained when the system gain, which is k in our case, is varied from 0 to infinity. Okay, so basically we will vary our gain from 0 to infinity and see what happens to our closed loop poles. And what are these closed loop poles? They are the roots of characteristic equation, and they determine whether our system is stable, unstable, or marginally stable. So this is a very, very important concept, this root locus, and it's actually a time domain technique. So it's a more generalized one, right? And the first type of questions that you have, uh, I don't know whether there is any question based on this in your assignment or not, but in general, your gate exam or anywhere where you are studying this root locus and you're being asked questions, the first type of questions is you're given a point, you're given a pole, or you're given a point. You're asked whether this point lies on the root locus or not. Okay, so I'll give you some point in the S plane and ask you, okay, tell me whether this point lies on the root locus or not, given this is your open loop transfer function, right? One more thing which is very, very important. When we are doing Raut-Hawitz criteria, we were saying the characteristic equation, which basically comes from the closed loop transfer function. But in root locus, we don't take closed loop transfer function. We just see open loop transfer function and start working. Okay, so that's one good advantage because it saves time. You just don't have to do that GS divided by 1 plus GSHS. So you can directly start from the open loop transfer function and you'll get insights about the closed loop transfer function from the root locus technique. So what I was saying, the first type of questions is you're given a point and asked whether this point lies on the root locus or not. So irrespective of what is the root locus, that doesn't matter. But yeah, you should be able to find whether that point lies on the root locus or not. So there are two conditions we check. So if those conditions are satisfied, then we say the root point lies on the root locus. One condition is called magnitude condition, and other condition is called angle condition, right? But before we go into the details, I'll just quickly, briefly tell you how we calculate the angles. You might have forgotten how we calculate angles in the complex plane. So then our things will be very, very easy because we can then straight away solve questions in a more easy way. So first, let's make the XY plane. Okay, so this is my X, this is my IY, or let's be very specific. Let's be very specific. This is my sigma, this is my J omega. That's what we see uh, in this is the S plane in this language. This is my first quadrant. This is my second quadrant. This is my third quadrant. This is my fourth quadrant. Another point which is very important is that we take angles positive when they are taken as counterclockwise and they are taken as negative when they are taken as clockwise. This is a general sign convention that we will follow. So perfect. So now this is a first, second, third, fourth. Now let's see. This is a complex plane, obviously. So you have a point here. This point is in a complex plane, so obviously it will be determined uh, by its magnitude and an angle, right? So here I'm interested in angles. So wait. Okay, so let's assume this makes an angle theta with this axis, with the sigma. So this is, let's name it as theta 1. And you see, I took it counterclockwise because then it will be positive. So I took it counterclockwise. And in general, if we have a complex plane, if it is x and this is iy, then this theta 1 will be tan inverse of y by x. Okay, but here I have this sigma and omega, so I'll directly write tan inverse of omega by sigma. Okay, so I can directly write tan inverse of omega by sigma for this angle here. Now, let's assume I have another point which is somewhere here in the second quadrant. How will I measure this angle? How will I measure this angle? Let's see. This is my angle. I will measure it like this. This is my theta 2. Okay, but I can also write it as this theta 2. I can write it as 180 minus theta 1. Okay, so if you see, I can write it as 180 minus theta 1. So in that case, my theta 2, I can directly write my theta 2 as, if you have a point in second quadrant, that no need to see, okay, how I can apply this formula, this and that. You can directly write that your angle will be 180 degree minus tan inverse of omega by sigma or of. Okay, so directly you can write. Similarly, in the third quadrant, okay, one more thing. This is 0 degree. This is 180 degree. And this is counterclockwise. If it is clockwise, then this is 0 degree, but this is minus 180 degree. And this was 90 degree clockwise. Counterclockwise, it's minus 90 degree. Or clockwise, it's minus 90 degree. Counterclockwise, it's 270 degree. So this 270 degree and minus 90, this is the same thing, right? So 90 and minus 270 is the same thing. And it's just a matter from where you are coming. Okay. So similarly, I'll not go into detail. I'll directly write theta 3. If it is in third quadrant, it will just be minus 180 plus tan inverse of omega by sigma. And this will be theta 4, which will be equal to minus of tan inverse of omega by sigma. So this is my fourth quadrant. So if I have a point in fourth quadrant, I can directly write the values of the angle from these formulas. Very simple. Now let's see one question, and that will make our things more clear, that about the questions, about the type of question that you get. And this is very famous these are very famous types of questions you get in your gate exam based on root logos. So if it's given, if g of s, h of s, that is the open loop transfer function, is equal to 1, no, it's k divided by s into s plus 4, then test whether S equal to minus 2 plus J5 lies on the root locus or not, and hence find the value of k. Pay attention. So let's solve it. So how we solve these type of questions? First, let me tell you. So that was we just discussed how we can find the angle and of in a complex plane. Now, for a point to lie on the root locus, the angle of GH directly, it should be it should satisfy the like for a point to lie on the root locus, it should satisfy angle condition and magnitude condition, right? So angle condition is angle of G of S H of S, it should be plus minus 180 degree or 2q plus 1 into 180 degree, or plus minus I can write. So what does it mean? It means the angle must be an odd multiple of 180. So angle must be odd multiple of 180 degree. Okay, so if angle is coming as odd multiple of 180, then we can say, okay, the root locus lies on the root, the point lies on the root locus where this q is 0, 1, and so on. Okay, this is angle condition, and the magnitude condition is magnitude of GH should be equal to 1. So let me write it. This is angle condition. This is magnitude condition. You just remember these two conditions and they will be very handy while you solve these questions. Now we just have to find the angle of this transfer function. So coming to the question, angle of G of S, H of S or GH will be angle of numerator divided by angle of denominator, right? So in the numerator, there is nothing, but first, this angle we have to evaluate where? At S equal to minus 2 plus J5. So put S equal to minus 2.J5. Wherever there is S, just put minus 2 plus J5. So I'll get K divided by minus 2 plus J5 into minus 2 plus J5 plus 4, which is equal to, let's simplify it a bit, K divided by minus 2 plus J5 into 4 minus 2 is 2 plus J5. So we have to find the angle of this transfer function. We have to find the angle. Okay. So see, in the numerator, there is no complex number. So in the numerator, the angle is 0. So it's the angle of GH is equal to 0. And the angles of the denominator, they will be subtracted because angle of any complex number, A by B is equal to angle of A minus angle of B. Right? So these things are very basic, so I'm not going into the details. Now see, what is the angle of this? What is the angle of this? So it will be, it is in this point is in second quadrant. If you see from here, we have minus sigma and plus j omega. So this is in second quadrant. So we can directly write sigma is 180 degree minus tan inverse of omega by sigma. That is 5 by 2. No need to take into consideration sine. Okay, it's already taken into consideration in this 180. Then again, um, this these are in multiplication, the angles will be added. So plus this is in first quadrant. So angle will be tan inverse of 5 by 2. This and this goes. So my angle of GH will be equal to minus 180 degree, which is odd multiple, of 180, because we can write it 1 into 180. Okay. So it means angle condition is satisfied. Therefore, the point is lying on the root locus. Done. So it had the system, the point has to satisfy the angle condition. Then we can say it lies on the root locus, and magnitude condition will be used to find the value of k. Okay. Now let's say the magnitude condition is g of h magnitude is equal to 1. And what is g in this g? So magnitude is k divided by minus 2 plus j5 into 2 plus j5 magnitude. So this should be equal to 1. So this will be k, and what will be the magnitude of this? This will be 2 square plus 5 square. 20. 2 square is 4, 5 square is okay, I'll just write minus 2 square plus 5 square into 2 square plus 5 square, which is equal to 1. This is 29 into 29, which is 29. So my is equal to k is equal to 29. So my value of k is 29, because 29 under root of 29 into under root of 29 is 29. So we get then, which is multiplied by 1. So we get k is equal to 29. Is this clear to everyone? Or I can explain it again. This will be, I think, more clear in this question. Just solve it. Your g of s, h of s. I want this time answer from your end. It's a good question. K divided by s plus 1 into s plus 2 into s plus 4. Find the point s equal to minus 1 plus j root 3, whether it lies on the root locus or not. Okay. And also determine k. Please, everyone, please solve it. Just do one thing. Wherever there is s, put minus 1 plus j3. I can write it. I can solve it and help you. If you see all the points, all these points are in the first quadrant. So you just have to write tan inverse of y by x. So the angle will be 0 minus, this will be 90 degree, because there is no real part. So tan of y by 0 is infinity, and tan is infinity at 90. So I directly wrote 90, then plus This is root 3 by 1. So it's 60 degree, tan 60 degree plus 30 degree. 9 threes are 9, 120. So this is again minus 180 odd multiple. Therefore, root locus lies on the, therefore point lies on the root locus. Point lies on root locus. Now you solve the value of k. Just find the magnitude, and then after you've put in the magnitude condition, that is gh is equal to 1, you'll find the value of k to be equal to 12. So I'll leave that as a homework. Just try. Now quickly, let's come to the construction of root locus. Do you want me to explain this a bit or directly solve questions? I think I can directly take a question because you might have gone through the lectures, so there is no need. But yeah, I'll go with a very basic question, which is k into s plus 2 into s plus 6, s plus 4, s plus 8. This is a very good question to start the construction of a root locus. First, tell me, now pay attention here. So we have, let's assume number of poles given by P. How many poles are there? There are 3 poles. 0, minus 4, minus 8. Number of zeros, Z, 2, minus 2, minus 6. Now remember, I'll just recap. A root locus always starts from a pole and terminates at a 0. So a root locus always starts from a pole and terminates at a 0, number 1. If you see here, so there are 3 poles, so the root locus will originate from 0, minus 4, and minus 8, and it should terminate at minus 2 and minus 6. And the number of branches of the root locus, they are given by the number of poles. So if the number of poles are 3, then there will be 3 branches of the root locus, right? So the number of branches which will terminate at, for this problem, at zeros are only 2. There is still 1 branch left because I told you the root locus, it starts from a pole and terminates at a 0. So 2 branches will start from the pole and terminate at 0, but because there are 2 zeros, but there is again 1 branch. Where will that terminate? That terminates at infinity, because we can treat infinity as a virtual 0. So you can, so that extra branch that terminates at infinity. And how that terminates at infinity? That goes to infinity via some straight lines, which are called asymptotes, right? So they go to infinity via asymptotes. And what is the angle made by these asymptotes, etc., we'll discuss. But for the time being, just let's just draw the root locus, right? So we will just make this S plane. Okay, so let's first of all, what we do, we locate these poles. We have a pole at 0. So we have 1 pole here. We have another pole at 4, which is here. We have another pole at 8, which is here. So we have 3 poles. Now we have zeros. We have zeros. 1 0 is at 2. So we have 1 0 which is here at 2. We have another 0 which is at 6, minus 6, sorry. So which is here. Okay, so I drew these poles and zeros. I'll just write this is sigma, this is j omega. Perfect. Now let's see. I told you a root locus always starts from a pole and terminates at a 0. And one more thing, this region, this whole region, this will be a part of root locus only if the pole, like a point on the real axis, it lies on the root locus if the number of open loop poles plus the number of zeros on that axis to the right side of that point is odd. For example, this region, if we have to see whether this region lies on root locus or not, we have to consider all the poles and zeros to the right of this point and see whether that is odd. If that is odd, the sum of poles and zeros, if that is odd, then this is a valid root locus. This is a valid part of root locus. This is a part of root locus actually. So I'm not going into the details. You have already gone through this in your lecture. So I'll just write. So this will be the valid region because there is one pole to the right of minus 2. This is minus 2. This is 0. This is minus 4. This is minus 6. This is minus 8. So a root locus, it starts from a pole and terminates at 0. Okay, it makes sense. And also there is only one pole to the right of minus 2, which is odd. So this is a valid area of root locus. Now let's consider the 0 at, let's consider this pole at minus 4. Now see, to the right of this pole, we have 1 0 and 1 pole. So it means the sum of that is 2. 1 plus 1 is 2. So it means that is an even number. So the region, this region for this part is this part then is not a part of root locus because we were considering minus 4 because the root locus actually it starts from a pole and terminates at a 0. So it should start here, somewhere here, but we just found out this is not a valid region for the root locus. Now, so it will then go somewhere here. Why? And terminate at minus 6. Why? Because if you consider this point minus 6, to the right of it, there are 2 poles and 1 0, the sum of which is 3. It means, yes, the point is this area, this region lies on the root locus, but it should start from a pole and or terminate at 0. So we draw it like that. Again, similarly, consider the point minus 8. To the right of it, we have 2 poles and 2 zeros. This is not a valid region, but yes, to the right of it, there is no 0, but it will indeed then terminate at infinity. So this will be valid region, and that will go to infinity. So this will go to minus infinity from here. Okay, so this should give you an idea like how we plot this root locus, because we just have to first of all plot the poles and zeros on the S plane, and after that we have to visualize it, like which area, which part will be valid part of root locus and which part will not be a part of root locus, and that is very well given by some set of rules which you already know. Now let's do one question where we see the angle of asymptotes, because this some branches in the root locus they do not terminate at zeros because the zeros are not there, so they eventually terminate at infinity. And how they go to infinity? They go to infinity by asymptotes, and we find the angle or angles of those asymptotes with the real axis. At the same time, we find the intersection of those asymptotes at the real axis on the real axis point, which is called centroid, right? So we will find centroid and we will find the angle of asymptotes. Then we will also see breakaway and break-in points. And that will be all for today. And in the next lecture, we will see problems based on angle of departure, angle of arrival, and other advanced root locus problems. Now let's solve a good problem. The question is, we're given a characteristic equation. Characteristic equation is given. I told you whenever we uh, talk of root locus, we talk of open loop transfer function. So 1 plus k into 1 divided by s into s plus 1 into s plus 2 is equal to 0. So clearly we can see from here, this is my g of s, h of s, because my characteristic equation is 1 plus g of s, h of s is equal to 0. And this is the open loop part, and this is what I need. And we have to draw the approximate root locus. We have to draw the approximate root locus. Now, see how we solve such problems. So whenever you have to find the root locus, see, go step by step. So see, first of all, you will see what is the number of poles? P, 3. What is the number of zeros? 0. What is P minus Z? 3. So it means the number of branches of this root locus will be 3, because that is given by the number of poles, and all these branches will terminate at infinity. Why? Because there is no 0. So they will all terminate at virtual 0, which is infinity. So the number of branches which terminate at infinity is given by P minus Z. And how they will terminate at infinity? Via asymptotes, and the angle of which we have to find out as well, right? That angle, you very well know that angle of asymptotes is given by 2q plus 1 into 180 divided by b minus z. Okay, what is q? Q is 0, 1, so on up to p minus z minus 1. Okay, so now see, I hope these things are already very clear to you. I'll just put in the values. So my p minus z is 3. My p minus z is 3. So I'll just populate this formula for q equal to 0, for q equal to 1, and for q equal to 2. That is what p minus z minus 1 is. 3 minus 1, that's 2. So my theta 1 will be 2 into 0, that is 0. So 180 over 3, which is equal to 60 degree. Similarly, my theta 2 will be 180 degree if you plug in the values, and my theta 3 will be 300 degree. In general, now, from now onwards, whenever you have a root locus problem and you have p minus z is 3, no need to calculate this angle of asymptotes. You know now the angle of asymptotes is 60, 180, and 300. So if you have number of asymptotes, if p minus z is 2, only 2 asymptotes are there, you know angles are 90 and 270, or 90 and minus 90. Okay, now see, what is the centroid? What is the formula for centroid? Centroid, which is given by sigma c, is equal to summation of real part of poles minus summation of real part of zeros divided by p minus z. So real part of poles, we have poles as minus 4 and we have poles at minus 1 and minus 2, which is actually the real part, and 0, which is not considered. So minus 1 minus 2 by 3, which is equal to minus 1. So my centroid is minus 1. So okay, now let's try to draw root locus for this problem. This will be very clear in a while. Just give me some moments. See, Let's populate. We have a pole at 0. We have a pole at -1. We have a pole at -2. Okay, so there is no 0. So the number of branches are 3. So there are 3 branches of this root locus. So, my root locus will originate from here, and also from here and here. Why? Because this is a valid root locus part, because to the right of it, there is only one pole, which is odd. So it's a valid point. This is not a valid part of root locus because to the right of it, there are two poles, the sum of which is even. So this is not a valid part, but this is a valid part. So I have root locus is something like this. So this will go infinity from here, but let me draw it like this. First, let's draw asymptotes, right? I told you the intersection of asymptotes is given by the centroid. So centroid is -1. Coincidentally, we have pole at -1 as well. So at this -1, it is the asymptotes are given by 60 degree. So 60 degree is something like this. Okay, this is 60 degree. Then we have 180 degree. So 180 degree is something like this. I'll draw it like this. This is 180 degree. And we have 300 degree, which is something like this. Perfect. Now this I drew the asymptotes, the angle of asymptotes. Now, see, this is a now when this root locus, this always starts from a pole and terminates to 0. When this root locus, it starts from here, and when the root locus is between two adjacent poles, then there is a break point, because this root locus will come here, here, and they will strike, and they will then strike and go to infinity, right? Because they will strike. So when they strike, then there is a occurrence of break point, and so it will be something like this. See, so here they will strike, and then they will go to infinity like this. Okay. Via these asymptotes. Okay. So j omega, this is sigma. Now see, can we find this break point? This actually, now what is happening? The branches are breaking away from each other. So this is called a breakaway point. But how do we find these break in or breakaway points? We will see. So now you see one branch is going to 0 via this asymptote, this 300 degree. Another branch is going by 60 degree, and another branch which is from here, it's going by 180 degree to infinity. So this is our root locus. But now how do we find this break point? This break point here, where this root locus goes to breaks away. Now see, pay attention. We were given the characteristic equation 1 plus k s into s plus 1 into s plus 2 equal to 0. What we do, we write this characteristic equation in terms of k. So I can write it k equal to -1 into s into s plus 1 into s plus 2. If I solve it, what will I get? Minus s square minus s, then s plus 2. Okay, so I'll get something minus s cube, then minus 2s square minus s square minus 2s. or which is equal to minus s cube minus 3s square minus 2s, or I get s square plus 3s s cube plus 3s square plus 2 equal to 0. If you solve it, no, now, okay, this is k. This is k. We got this k. Now, what we have to do after this, we have to differentiate this k with respect to s. So dk by ds and put that to 0. So what is my dk by ds? It will be 3s square plus 6s plus 2. So this is my dk by ds, and when you put equal to 0, you solve it, you will get s equal to minus 1.57 and minus 0.423. So these are my breakpoint candidates. These are my breakpoint candidates. But see, the breakpoint will occur between s equal to between minus 1 and 0. Okay, and the valid breakpoint in that case is only this minus 0.423. Okay, so this is a valid breakaway point. So this point here, sometimes you are being asked, find the value of this breakaway point. So it is minus 423. What you have to do, just find the expression for k, differentiate that with respect to s, put the value of s to 0, and find the value of s. From that, identify the proper candidate. I hope things are now slightly clear. So if that is the case, can you just solve this last question and then we can stop. What I assumed is that you have already gone through the lectures and the slides. Otherwise, I would have I would have revised, but then it will take a lot of time and we will not be able to solve more and more questions. Last question for today is, we are given an open loop transfer function. This is a very interesting question. We have something in it. S into S plus 2. Can you draw the approximate root locus and tell me whether there is any breakpoint? What is the centroid? Okay, no, okay, I'll help you. Solution. P is 2, 0 and minus 2. These are the poles. So the branches will be 2. It means 2 branches. Z is 0. No, there is, it means both these branches will go to infinity, it will terminate to infinity via asymptotes. And what will be the angle of those asymptotes? Theta will be 90 and minus 90, or 270 degree, because obviously when you put in the values, you will get theta as 90 and 270, or 90 or minus 90. Let's put in, okay, now centroid. Centroid, when you put a real part of poles, 0 minus 2 by 2, which is minus 1. There are no zeros. So centroid is also minus 1. Now let's draw a rough sketch. Sigma j omega. Where are the poles? The poles are at 0 and the poles are at minus 2. This is minus 2, this is 0. What is centroid? The centroid is minus 1. I'll not mark it. This is my centroid, which is minus 1. Okay. Now you see, from the centroid, there will be 2 asymptotes. I'm drawing them like this, from where my branches will go to infinity. So my branches will be somehow coming from here, then going like this, and going like this. It can be like this. But let's analyze, because the root locus is between 2 poles, so there has to be a break point. Okay, there has to be a breakpoint. So let's find that breakpoint. So we will find the value of k from here. So first we'll find the characteristic equation. So my characteristic equation will be 1 plus k divided by s into s plus 2, which is equal to 0. From here, I will find my k is equal to minus s into s plus 2. You find k equal to minus s square minus 2s. dk by ds is equal to minus 2s minus 2. Put this equal to 0. It implies 2s minus 2 equal to 0. Sorry, 2s equal to 2. 2s equal to minus 2 and s equal to minus 1. Okay, so now see, my centroid is at minus 1. I'll write this is minus 1. And my breakpoint is also at minus 1. So this is a unique scenario. It comes sometimes. So that means now my root locus will come. My root locus will come from here, from here, from here, from here, also from here. But it will go to infinity via asymptotes. It will go to infinity via asymptotes. Why? Because here my centroid and breakpoint they coincide. So whenever my centroid and breakpoint they coincides, branches break along asymptotes. So if you see here, I wrote it like this. I wrote it like this. I made it like this. Why? Because they will go to infinity along asymptotes, but not like breakaway point that will take the direction given by asymptote. But here, the points they will break along. They will break along the asymptotes, right? So there is nothing fancy like this. You'll see in the next week or something like this. You'll see in the next week that maybe in some cases you get a root locus like this. They go to infinity like this, and that other goes to infinity like this. Okay. So one important takeaway is that whenever centroid and breakpoint, when they coincide, uh, the branches break along asymptotes. So now one last point, and at that point we will end today's lecture is that, see, this is my breakpoint. From this breakpoint or um, centroid, so there are only 4 directions. There are few directions, or okay, that we'll discuss. I need something for that, so that we can discuss in the next lecture. We will uh, see angle of departure, angle of arrival, and also intersection of this root locus with the imaginary axis, etc., and solve some of the good problems. So that will be the content for the other week. Next week, we might also see complementary root locus. But for the time being, I'm just concluding it here that basically, we learned some of the rules of root locus or how we can draw root locus, how to find centroid, how to find asymptotes, angle of asymptotes, the number of asymptotes and their angles, and how the when does the break away or break points actually, when do break points occur? This is basically break away point. We will see something called break in point as well. So, but yeah, before I end today's lecture, we'll just discuss one thing: why this breakpoint occurs, right? So, if you see the characteristic equation of this problem, this characteristic equation is 1 plus k divided by s into s plus 2. If we solve it, we get s square plus 2s plus k equal to 0. So the second order system, obviously, we will have 2 poles. Okay, so let's take k equal to 1. When we take k equal to 1, what we will get? S square plus 2s plus 1 equal to 0. If you solve it, we will get s plus 1 whole square is equal to 0. It means s equal to minus 1 minus 1. It means I got repeated roots. So in root locus, what we do, we vary this k from 0 to infinity and see the locus of the roots. So at one point of k, at one value of k, we are getting repeated roots. So this occurrence of repeated roots is the reason behind breakpoints. So whenever there is a breakpoint, you should assume that, okay, some value of k is given repeated roots. There are repeated roots at minus 1. So that's why these breakpoints occur. Or in general, you can just see it from the root locus that whenever whenever there is a valid root locus between two poles, then there will be a breakaway point, or like there will be a breakaway point, because obviously this root locus, they will strike to each other. That's all for today. If you have any questions, please ask. Otherwise, I can. Okay. Shubham is saying how to find centroid. I'll just do that. See, what is the formula for centroid? The formula for centroid is summation of real part of poles minus. I'll write the formula. Okay, centroid. This centroid is given by sigma c. It is equal to summation of real part of poles minus summation of real part of zeros divided by p minus z. Now let's come to this question, which was, what was it? It was when g of s is k divided by s into s plus 2. I think this was it. Now let's find the centroid. What are the poles? 0 and minus 2. Both are real. What are the zeros? No zero. So what will be centroid? Sigma c will be a real sum of real part of 0. So 0 is 0, 0 plus minus 2 is minus 2. So this is summation of real part of zeros, then minus summation of real part of zeros. There is no 0, divided by p minus z. P minus z is 2 minus 0. That's 2. So 0 minus 2 is minus 2, and 2. This will be minus 1. Is that clear, Shubha? Summation of real part of poles minus summation of real part of zeros divided by p minus z. Is that clear? If you have any other doubt, please ask. Otherwise, we can just stop. Physical significance, it's just the intersection of the asymptote at the real axis. So you see, we draw this root locus or the other root locus. Yeah, or take this example. We draw this root locus. So we saw there are 3 branches which will terminate at infinity rather than on any 0, right? But when they terminate at infinity, they have to terminate through s. They will asymptote. They will terminate through via these asymptotes. Okay, but these asymptotes, they have to, like, how we can draw these asymptotes? Like, they are making some angle with the real axis, but at which point? At which point we can, so we found the angle made by asymptotes. So where exactly on real axis do these asymptotes make the angle? So that is given actually by centroid. Okay, so in the other case, you can just Um, yeah. So we will also be taking this root locus again in the next week, where we will solve some of the very good problems where a root locus can be a circle or other good shapes, and solve some angle of departure, angle of arrival problems, which are actually asked in questions. But yeah, this magnitude condition, angle condition, they are also very very important, and mostly you get questions from them. And we will also be doing, I don't know whether that is in the syllabus or not, the control design by root locus, because uh, we are actually varying k. So from this root locus, we can stop at that value of k where we are getting less overshoot, more rise time, or whatever is the design specification. When we traverse through the root locus, we can stop at that point where we are getting the desired uh, specifications. So that will be also a topic for the other day. So for now, thank you very much for attending this session. Uh, we'll see you in the. I'll see you in the next week. If you have any question, please ask.
Thank you, sir. Yeah, thank you, sir.
Yeah, thank you.